Hello, today we will start with endocrinology. These are Dam's notes of physiology and the chapter is endocrinology. We will start with, let me bring it closer. We will start with the uh, classification of hormones which are based on solubility. They can either be lipid soluble or water soluble. Lipid soluble hormones, they are steroid and thyroids. See, lipid, LIPD, it ends with the word lipid ends with D, steroid ends with D, thyroid ends with D. This is the way I have memorized it. Lipid soluble hormones, they are synthesized as when needed. Means there is no storage except for thyroid, because we all know thyroid is stored in thyroid follicles. Lipid soluble hormones, since they are lipid soluble, they are not water soluble, so they need some protein to be transported, and they do have receptors, cytoplasmic and nuclear receptors. Mnemonic, which helps us to remember substances which do have cytoplasmic or nuclear receptor, is DATE, D-A-T-E, DATE. Vitamin D is DATE, D. D is vitamin D, A is vitamin A, T is thyroid and testosterone, E is estrogen. Means all these substances, they do have cytoplasmic and nuclear receptors. Coming to water soluble hormones, they are amines and peptides. They are synthesized and stored. Unlike lipid soluble hormones, which are not stored, these water soluble hormones, they are stored. They are transported as such, because they are water soluble. They don't need any transporter except insulin like growth factor. It needs some protein to carry it. And they do have membrane surface receptors. They use second messengers except insulin, because insulin does not need second messenger, since insulin receptor itself has tyrosine kinase activity. And when we talk about a total hormone, they include bound hormones, which are bound with the albumin, and free hormones. It's the free hormone actually which is active, functionally active hormone, and they do have negative feedback effect. Next thing what we have to learn is liver inducers and inhibitors. Liver inducers are the substances which increase activity of liver. When liver activity is increased, it obviously increases the protein manufacturing, um, and which in turn increase the bound hormones, and for a transient period it decreases free hormone. That means with liver inducers in our body, our total hormone level is increased, bound hormone level is increased, and free hormone is normal. And we should know what are these liver inducers. There's a mnemonic, coprime. Coprime. Well, this is my very absurd mnemonic, I know, but seriously, quickly I couldn't think of anything else. Maybe this will help someone. Co is clofebrate, O is opioid derivative, P is phenobarbital, R is rifampicin, E is estrogen, M is methadone, and major tranquilizers. Coprime. Co here is an English word which means sort of together. Prem is a Hindi word. More or less they are same words. Coprime. Okay. And inhibitors of liver activity, or we can say substances which inhibit action of liver and decrease protein output, they are danazole and asparaginase. How do they work? They can decrease total hormone levels in our body, they can decrease bound hormones, but still free hormone is normal. Next, what we all know is hypothalamic hypophyseal axis. Hypothalamic hormones, they do have pulsatile release except for thyroid. Uh, uh, gonadotropin releasing hormone. If we give low frequency pulse, it favors the secretion of follicular stimulating hormone, but at the same time, high frequency pulse favors secretion of luteinizing hormone. What if we give constant infusion of gonadotropin releasing hormone? It decreases both follicular stimulating as well as luteinizing hormone levels in our body. Pulsatile release of gonadotropin releasing hormone, what they do, they prevent down regulation of its receptors on gonadotropes of anterior pituitary. Pulsatile release of gonadotropin releasing hormone prevents down regulation of its receptors on gonadotropes of anterior pituitary. Now we are going to start with the pituitary hormones, anterior pituitary as well as posterior pituitary hormones. Here I would like to add that pituitary is a gland which is like approximately, if I remember it right, 0.5 grams in weight. It weighs 0.5 grams, though it's such a small, seemingly small organ, seemingly small gland, but it's a master gland, and it is really very important in our body because it's with the help of this hypothalamic pituitary, hypothalamic hypophyseal axis, hypothalamic pituitary axis that our glands hormones are controlled and our body is able to function properly. So when we talk about pituitary gland, it has two lobes, anterior lobe and posterior lobe. Posterior lobe is also called neurohypophysis. Anterior lobe, which contributes approximately 80% of the secretion and 80% of the secretion of the hormones, and posterior lobe, it contributes small but very important contribution. It has, it's 20% secretion, but posterior lobe, which we are going to read little bit later, it secretes oxytocin and ADH, antidiuretic hormone, and both of them, they are stored in special kind of axonal endings. Basically they are the terminal ends of axons from hypothalamus, and we call them herring bodies. So anterior pituitary, it has it's written in our notes, it has two types of major cells, acidophils as well as basophils. Then acidophils, further they are somatotrophs and lactotrophs. Soma, which is a body, means somatotrophs, they release growth hormones. Lactotrophs, they release prolactin. Okay, basophils, they have corticotrophs, gonadotrophs and thyrotrophs. Corticotrop, it releases ACTH secretion. Gonadotrophs, they have FSH and LH secretions. And FSH and LH we have already read, it has pulsatile release. Low frequency will help it to release FSH, while as high frequencies and high frequency pulse of GnRH favors LH release. Thyrotrop, they secrete TSH. Okay, here I would like to add something over here, that excess of secretion of pituitary or decrease or deficiency of pituitary hormones, they give rise to certain diseases in our body, which are very important diseases, which we do have to read in pathology. And the cause of pituitary decrease of pituitary hormones, or even its excess, can be anything. It can be maybe adenoma, maybe surgery, or radiation, or ischemia, or there is this thing called a Sheehan syndrome or NPT-SILA, anything. Decrease of pituitary hormones, like pituitary hormone, we know it's growth hormone. It's when the secretion of growth hormone decreases, it gives rise to growth failure. There is growth failure, and they can be hypogonadism, they can be hypothyroidism. These are the clinical features of hypopituitarism. Hyperpituitarism, obviously it can cause like see, lactotrophs, they secrete prolactin. If excess of prolactin is there in the body, it can give rise to prolactinoma. which is basically a microadenoma, and a person can come with the complaints of amenorrhea, galactorrhea, or infertility. Okay, excess of growth hormone can lead to gigantism, which is a excess growth hormone condition in children, and or acromegaly, which is a excess growth hormone condition in adults. Though both of these conditions, they are most of the times they are associated with other conditions like diabetes, muscle weakness, hypertension, or CHF. Okay. Growth hormone secretion. The stimulus of growth hormone secretion, it can be fasting, starvation, hypoglycemia, stress, emotional stress, stage 3rd and 4th of non-rapid eye movement sleep, or exercise ghrelin secretion. Okay. um, Stress hormone, actually they increase energy substances, glucose and fatty acids. Stress hormones, they are catecholamines, growth hormone, glucocorticoids, glucagon. So there are G3, growth hormone, glucocorticoid, glucagon, ADH, and thyroid. Sometimes it has both catabolic as well as anabolic effects on our body, depends on the concentration of thyroid hormone. Growth hormone action can be studied under two headings. See, what's written in the notes, it's direct effect and then we have indirect effect. Direct effect, if we say it simply increases blood sugar levels, which is an anti-insulin property or anti-insulin function of growth hormone. Then it increases free fatty acid levels in our body, that is lipolysis. It increases protein synthesis. It increases calcium, phosphorus, sodium, potassium retention in our body. It helps in chondrogenesis, and at the same time, when we if we read indirect actions of growth hormone has an indirect action via insulin, like growth factor 1, which is also called somatomedin C. What it does, it decreases blood sugar levels, it causes lipogenesis, increase in protein synthesis as that of direct action, it causes chondrogenesis as that of direct action. Okay, quickly we are going to read about the prolactin excess. There are conditions which cause prolactin excess in our body, and we can remember it by the mnemonic like new pets shop. New pets shop is a mnemonic. New is nursing period, P is pregnancy, E is estrogen, T is TRH, S is sleep, S is stress, strenuous exercise, sexual intercourse, H is hypothyroidism, O is opioids, and P is phenothiazine. These are the conditions which increase prolactin hormone secretion in our body. There is something which I would like to add over here. It's Nelson syndrome, which is not shown in this note, but maybe there will be some question on it. Maybe, may not be, I don't know. That is Nelson syndrome. Nelson syndrome is actually I found it quite interesting. That's what I would like to share over here. Nelson syndrome is it's actually surgical removal of adrenal gland. When we remove surgically adrenal gland, it stops giving inhibitory signals to pituitary, and as a result there is increase in pituitary corticotrophs, and as a result we see ACTH adenoma. So this was something which I found quite interesting. And okay, so next is posterior pituitary. Posterior pituitary, as I have read, I showed you posterior pituitary. What it does, it releases oxytocin and antidiuretic hormone, and posterior pituitary It's also called neurohypophysis. It contributes only 20% of the pituitary hormonal secretion. Both oxytocin and as well as ADH, they are actually stored in herring bodies, which are axonal ends, terminal ends of axon. Okay. Posterior pituitary. What's written in the notes is the stimulus which increase antidiuretic hormone. um, and the stimulus is increase in plasma osmolality, a decrease of blood volume. Uh, but there should be 10 to 15% decrease in the blood volume. Only then it will be able to produce decrease in antidiuretic hormone, which is basically a compensatory mechanism of the body to prevent further loss of the fluid from the body. Trauma, surgery, pain, nausea, vomiting. Let me read it once again. Uh, Increase in plasma osmolality, decrease of blood volume, trauma, surgery, pain, nausea, and vomiting. They are the conditions which actually increase ADH secretion. Emotional stress and prolonged stranding also result in increase of antidiuretic hormone secretions. Antidiuretic hormone deficiency or decrease in the secretion of antidiuretic hormone, it can be because of obviously the reasons opposite to previous opposed to what we just read. They can cause decrease in anti-ADH secretion, like decrease in plasma osmolality or increase in blood volume. And there is this interesting thing which is weightlessness. That is when we immerse ourselves into the water up to neck, maybe in the pool, we have decreased ADH secretion. And consume when you consume alcohol. Okay, those who consume alcohol, they also do have decrease in ADH secretions. In fact, ADH deficiency can lead to diabetes insipidus, while as its excess can lead to a condition called SIADH, syndrome of inappropriate antidiuretic hormone. ADH deficiency is something which can cause increase of sodium because of the failure of renal water absorption. In antidiuretic hormone deficiency, there is failure of renal water absorption, which causes increase of sodium and can result in polypsia or polyuria. Okay. ADH deficiency or diabetes insipidus can be because of head injury, tumor, inflammation, or that pituitary hypophyseal surgery. Okay. And when we talk about SIADH, syndrome of inappropriate antidiuretic hormone, it causes increase of renal water reabsorption, and obviously there is decrease of sodium. SIADH can result in neurological manifestation, and the most common cause is ectopic ACTH, maybe in lung carcinoids or pulmonary TB or pneumonia. This is something I would like. I just added into this physiology notes. Receptors of ADH, they are V1 receptors and V2 receptors. Basically, vasopressin. ADH is also called a vasopressin. The V1 receptors, they are further classified into V1A and V1B or V3. Okay, V1A, they are present in blood vessels which have vasoconstriction effect. Visceral smooth muscles, they also cause contractions. They are present in liver, they cause glycogenolysis, and in platelets they cause platelet aggregation. Sorry, it's not aggregation, it's aggregation. V1B or V3 receptors of ADH, vasopressin receptor, also called V3, they cause anterior pituitary release of ACTH. V2 receptors, on the other hand, they are present in kidney, and they cause increase in water permeability. They are present in blood vessels, cause vasodilation. They cause release of von Willebrand factor, factor 8 from endothelium. This is, I think, very important point, that they cause release of von Willebrand and factor 8 from endothelium. What is the next thing? Next thing is thyroid hormone. Thyroid hormone. Now we have to start with the thyroid. Thyroid, I would like to add that it's 15 to 25 gram gland. It has two types of cells: follicular cells and parafollicular cells. Follicular cells which cause the synthesis of or release of T3 and T4, which are thyroid hormones, while as parafollicular cells, they cause calcitonin release, which decrease the calcium. We have to read about the synthesis of thyroid hormone. Actually, I'm not going to continue with the word-to-word reading of this note. Let me put it into my own words, which I have studied or read from other books or other sources. You please try to just listen to it, because if I write, it will take some time. I don't want to prolong this video. Maybe there are students, there are friends who are just listening. They may not need this visual thing. They may be just listening to me. So I will just try to make it very fast. Thyroid hormones, they are actually anabolic hormones, but excess of them can lead to increase in catabolism. And thyroid hormone, we all know, they are very, very important for mental and physical growth of our body. They are very important for maintaining sensitivity of adrenergic system, and definitely they contribute in basal metabolic rate. Thyroid, we all know they are present in front of trachea and below larynx. It has, like pituitary, it has two lobes, and both lobes have isthmus in between. Thyroid gland is composed of follicles, which are made up of thyrocytes, epithelial cells, which are basically like cuboidal cells. In between stroma, there is capillaries present. Follicles basically, okay, maybe it will be a little bit easy. We have follicles, we have parafollicles. Follicles, pardon me for wrong spelling in case. Follicles, they are they do secrete T3, T4, while as parafollicles they are responsible for the secretion of calcitonin and T3, T4. Okay, and T3, T4 has a property: it acts on every single cell of the body. Okay, what the cuboidal cells actually do? Cuboidal cells, what actually they do? Which are basically cells of thyrocytes. We can call them as maybe unit of thyroid hormone, functional unit of the thyroid hormone. We may call them as. What these cuboidal cells do, they have. I'll try to make it extremely brief. What they do, they actually take iodide from the body. They take iodide from the body, which is the raw material. They synthesize thyroglobulin. They synthesize thyroglobulin, and they cause thyroglobulin plus iodine. They cause monoiodothyronine or diiodothyronine, in tetraiodothyronine, monoiodothyronine or diiodothyronine, okay, which result in formation of T3, okay, or diiodothyronine plus diiodothyronine, they synthesize T4. Monoiodothyronine and diiodothyronine, they form T3. Diiodothyronine and diiodothyronine, they cause T4. I know it's a little bit confusing here, but let me try to make it a little bit simpler for me, for you also. Actually, the iodine which is consumed by our body, the 100% iodine which is consumed in the diet is in iodide form, and only 20% is taken by the thyroid. The rest 80% is waste, okay. Since iodine, it's a charged molecule, so there are special pumps or iodine pumps that are present on the walls of follicles. What they do, they take iodine from circulation into the cells via active transport mechanism, and there is a enzyme in the lumen of the follicle. It converts iodide into iodine, and there is this enzyme peroxidase. Iodide is converted into iodine with the help of peroxidase. With the help of peroxidase, or we can call it thyroid peroxidase. Thyroid peroxidase. Thyroid cell also form thyroglobulin. So what we have there in the follicles, what we have in the follicle is okay, we can call it structural and functional unit of the thyroid gland. What we have there in the follicle, we have iodine. From the diet, we have this thyroid peroxidase. We have iodine, we have thyroid peroxidase. Then we have something which is called thyroglobulin. Which is synthesized from a gene. Basically, gene give rise to special messenger RNA, which is translated into thyroglobulin, and thyroglobulin has tyrosine residues. This thyroglobulin, which is there present in the cuboidal cells, epithelial cuboidal cells, which are the cells of follicle. This thyroglobulin, it has tyrosine residues. It has tyrosine residues which goes into the endoplasmic reticulum. It gets glycosylated and packed into vesicles, and then they are released into the luminal area. Okay, this thyroglobulin has tyrosine residues which goes into the endoplasmic reticulum, which gets glycosylated and are packed into the vesicles. I have tried to make it as simple as possible. Okay, which are packed into the vesicles and are released into the luminal area. So this thyroglobulin, now what we have there in the follicle, we have iodine in the follicle from the diet, we have thyroid peroxidase in the thyroid follicle, we have this thyroglobulin which are made from the gene which makes special messenger RNA translated into thyroglobulin. Okay, with these three things there in our follicle, what actually happens, thyroglobulin plus iodine from the diet with the help of peroxidase, it forms monoiodothyronine. Monoiodothyronine peroxidase. So iodine is translated into iodide is changed into or transformed into iodine with the help of peroxidase. Plus this iodine is coupled with tyrosine with the help of peroxidase. So this is the second function of peroxidase. Okay. If one tyrosine of thyroglobulin it combines with the one iodine molecule, it forms monoiodothyronine. But at the same time, one tyrosine plus two iodine molecules, they form diiodotyrosine, and both of them are because of peroxidase enzyme. Okay, now this, if two monoiodothyronine, they are combined, they form monoiodothyronine, they form and one monoiodothyronine monoiodothyronine plus diiodothyronine. Monoiodothyronine and diiodothyronine, they form T3, and at the same time diiodothyronine plus diiodothyronine, they form T4 with the help of peroxidase. And both this formation is in thyroglobulin. It is within thyroglobulin. So peroxidase enzyme, first thing is it helps in transformation of iodide into iodine. Second thing is it forms coupling of tyrosine molecule, tyrosine residue of thyroglobulin with iodine. Third, it forms again coupling of monoiodothyronine with diiodothyronine or diiodothyronine with diiodothyronine. It helps in the formation of T3 and T4. Okay, so this was maybe brief introduction of this